So electrochemistry is all about using electricity and chemistry together. So electrochemical cells are devices that are doing one of two things. You're either using the chemical energy to get electrical energy, which we call a galvanic cell, or you're using electrical energy to force a chemical reaction, and we call that an electrolytic cell. So galvanic cells are used in things like batteries, where the chemical energy by way of redox reactions creates moving electrons, which of course is electricity. And electrolytic cells are used for things like extracting metals from their ores and things like that. So you have to force the energy in there, force the electrons in to try and separate the metal. So what one of these will look like in the lab is something like this. There'll be a beaker, two beakers. There'll be some metal things, so that's what these bits are, the metals. There'll be wires joining the metals, and there'll be a voltmeter to measure the current. And once it's all set up, it'll look something like in this picture. So you can see the strips of metal, the voltmeter with the wires to show you, what kind of current and voltage you're generating, as well as some other things that we'll go into more detail about now. So if you want to just pause the video and get a diagram like this copied down, and then we'll put some labels on each of the things. Alright, so on either side here, we have what we call electrodes. So this is the name of the metals that are doing the electron transfer. Now connecting them are wires, and often or generally they're connected by alligator clips, which you can see in the picture there. So you alligator clip the wires onto the electrodes. Now in between the electrodes you will have a voltmeter to measure voltage, or perhaps an ammeter to measure the current. So a voltmeter is about like how much energy the electrons have, and ammeters is about how many electrons are moving. Now the electrodes sit in a solution that we call an electrolyte. And over here we have an electrolyte. And the final thing that you'll see here is called a salt bridge. Now the salt bridge is there because for electricity to flow you need a complete circuit. So if the energy starts in here, or the electrons, and comes up around here and into here, and then it would stop without the salt bridge. So the salt bridge is there so that the flow can continue, and that will create a circuit, and then the electrons will be able to continue flowing around. Without that, you'll get no electron flow at all. So it would just do nothing really without the salt bridge. It's very important. All right, so now what we want to look at is an example of a galvanic cell set up with specific metals. So what we're going to look at is a galvanic cell set up for magnesium and silver electrodes. So if we make this our silver electrode, then this would make it a magnesium over here. Now the more reactive metal will be negatively charged, because the more reactive metal will be losing the electrons. So electrons will flow away from the more reactive metal. So magnesium is more reactive. It will carry a negative charge. And silver is more positive. The electrons are going towards it. It must be positive. All right? Electrons will only flow towards positive and away from negative. So the way the electrons are flowing must be this way. They're going to go from the more reactive metal to the less reactive. And we have a special name for the each electrode, depending on whether they're positive or negative. So the negative charged electrode is called the anode. And you've probably noticed that anode shares the same prefix as anion. So anions are negative, anode is the negative electrode. And you can probably predict that then the silver one, which is positive, will be called the cathode from cation. So cations are positively charged, cathodes have a positive charge. Now the electrolytes are not always, but generally the electrolyte will just be a solution containing the ions of the metal that is in there. So our electrolyte here has magnesium ions in it. Which basically means there's a lot of Mg2 pluses floating around in there. And over here we have a silver electrolyte, which means there's a whole bunch of Ag pluses floating around. And, you know, of course, there'll be a salt bridge. The salt bridge, what's actually on it doesn't matter so much, as long as it's something that will let the electron flow continue. So if you, when you do the prac, you'll make your own salt bridge out of potassium nitrate, I believe. But it doesn't matter what you put on the salt bridge, as long as it is something that's going to be able to carry the electron charge. All right, so we've got a lovely labeled diagram. The electrons are going to flow from the magnesium electrode towards the silver electrode. And now we want to know what's going to happen at each electrode. Which one's going to get built up? Which one's going to break down? So at our anode over here, there'll be a certain reaction, and at the cathode, there'll be another reaction. Now, to figure out which metal is going to be losing the electrons, we look at our reactivity. So magnesium's more reactive. It's going to lose electrons to the silver electrode. So that means that magnesium will start as an start as a solid, and it will become an ion because it loses electrons. And the cathode, the silver, that's going to do the opposite. It's less reactive, so it starts as an ion and it becomes an atom, an uncharged atom. Now these equations aren't balanced, so we also have to show that there'd be electron transfer happening. So this gives us a good description of what's going on. Magnesium, the solid, is going to send off electrons, so they'll go up along here to the silver. Oops, it's on the wrong side. So the electron comes along into the silver to create silver as an uncharged atom, and that will start building up on the silver electrolyte. Sorry, on the silver electrode. And there's a better way to represent that than these equations. Well, maybe not a better way, but a shorter way. So the way we could also represent it is that Mg goes to Mg2 plus, and the line represents the fact that there's a boundary between the electrode and the electrolyte. And Ag plus is going to Ag. So something you might see at the anode is that it gets eaten away because the magnesium is being turned into magnesium ions, and then they'll disappear into the solution. Something you'll see at the silver electrode is that it starts building up because the silver electrolyte stuff is being pulled out of the solution and into solid silver. So we can combine this all into one equation to show us what's happening in the whole process. So we can write that Mg plus 2 lots of E minus, so we'll make 2E minus so that that matches up, and that would also give us 2 Ag plus to create Mg2 plus 2 lots of Ag plus 2 lots of E minus. Now we could cancel them out, and so really the result of this galvanic cell is that the magnesium is reacting to form a magnesium ion, and the silver ion is reacting to form just an uncharged silver element. Like so. So that is the basics of galvanic cells. So the key things to remember: the anode is negative, the cathode is positive. The anode is more reactive, which means it will be oxidized, and the cathode is less reactive, which means it will be reduced. And you can look at your equations to see that without necessarily remembering it or memorizing it, because magnesium is losing electrons and that makes it oxidation, and silver is gaining electrons, which makes it reduction. Remember your oil rig. All right, so that should help you when you come to do the prac with being able to draw your diagrams and labeling all the different parts.